Good afternoon, everyone. Thank you so much for joining us today. I know it's a first session post-lunch, so I might expect a few drowsy faces. But don't worry, I'll make sure to keep this session engaging. We have some interesting sessions and we have some interesting lessons and stories to talk about during the past 1 year of CRI-O development. As you might have seen, and this is our day one at KubeCon, there are a couple of AI talks, and AI is everywhere. So there's a different excitement on how AI is actually building things around Kubernetes. Let that be AI workloads, AI demos, AI tools, and the dust is settling down, and we are seeing the real production workloads in production. But at the same time, we want to make sure that the business critical workloads are running fine and they have a certain threshold. And that's where the CRI-O's philosophy is very simple, one container at a time, where we want to make sure that things are running fine, and at the same time, we are also supporting the growing needs of the business where, the future things that we have. So with this, I want to introduce myself. I'm Sohan Kunkerkar. I work at Red Hat as a senior software engineer. I'm one of the CRI-O maintainers and involved in the upstream SIG-Node initiatives. I recently started working on Q. It's a job manager for Kubernetes, and which also intersects with Red Hat's AI initiative. So with me, we have...
Yeah, I'm Ayato Tokubi. I'm also a software engineer in Red Hat, and I'm also a reviewer in CRI-O.
All right. Thanks, Ayato. All right, so I'll quickly walk you through what we're going to cover today. I know most of you are already familiar with CRI-O. If not, I'm going to talk about the introduction, followed by the lessons that we learned over the past 1 year in the CRI-O development. Then we recently inducted one project in CRI-O community called CRI-O Credential Provider. We'll have some information about that. And then we'll talk about some of the upstream SIG-Node initiatives that we are taking into consideration and the features we are building around that. And then comes the most awaited feature, that OCI volume image that Ed is going to cover with the help of demo. And towards the end, we're going to talk about the future roadmap and having closing remarks, and we'll open up for questions. Sounds good? Perfect. Can I get a quick show of hands? How many of you are aware about CRI-O? Perfect. For those who are not aware about CRI-O, CRI-O is a container runtime specifically designed for Kubernetes. It basically complies with Kubernetes container runtime interface, where you can see the acronym CRI, and O stands for open container. So in a nutshell, you can say CRI-O creates the pod, it runs the container, and it spits the logs where you need to see it. So ultimately, you can think of it as, in CRI-O, we believe in balance. At the same time, we focus on security, and it also supports the OCI-based image registry and runtimes. So our focus is mostly around development, innovation, but we need to make sure that we are building features one at a time with some testing. So at later point of time, we don't need to kind of regret on the edge cases that we kind of encounter at some point of time. And last but not the least, but very important, CRI-O is a CNCF graduated project which defines its maturity, and that's why it has a wider adoption across both OpenShift and Kubernetes ecosystem. All right, so here I want to take a pause and probably want to discuss about the decision that we took last year during KubeCon Salt Lake City, where we made an announcement of making CRN as the default runtime. We often discuss about new features. We often neglect the lessons, but here I want to start with the lessons. And that's how we grow the community and build the community. So for those who don't know about CRN is the lower level OCI container runtime written in C. It's an open source project. And the primary motivation behind making CRN as the default runtime, it's because of the performance, then lower memory footprint, and last but not the least, it supports advanced workloads, something like WASM, confidential containers. So we actually done a couple of performance improvement tests, and every time we saw faster pod startup times and reduced overhead. and that too across hundreds of pods on a node. So that's where we thought of making Siren as a default runtime, and we saw that improvement immediately when we upgrade the cluster from Runc to Siren. And the foundational part of it is like we basically build that foundation to make sure the end users can run next level workloads. But as you might have expected, like with this decision, there was room for some improvement, and there was something during testing that we didn't encounter before. So that is what triggers us, and that's what the lessons that we want to talk about today. All right, so what really happened here? We basically changed Siren to Runc, Runc to Siren, which was the easy change. But what we really did there is like we changed the system where Runc has been tested, battle tested against the upstream Kubernetes CI for a longer time. So Runc was actually run against all types of pod lifecycle edge cases for a long period of time. Siren, on the other hand, is simple, faster, and advanced. But we tested against CRI-O, but there are a few use cases where we thought we would have covered in the Kubernetes upstream CI. And we started that initiative recently. So we started seeing this behavioral difference in the runtimes where both are using the same features, but there were some different assumptions. I'll give you an example in that. So we recently found out there was an upstream Kubernetes conformance test, which was failing for Siren. And that was around summary API, which was actually counting the process count. Now, for Runc, they were unconditionally setting the resource accounting. So CPU, memory, I/O task. So if you look at Siren, the logic of Siren, they were setting those properties only when the resource is defined for that particular. So Siren is not wrong in the logic. They were right, but when you talk about the kernel, the resource accounting will deviate depending on whether whether the resource is defined for that particular period. On the other hand, if you talk about Runc's always-on behavior gave the consistent behavior on the upstream Kubernetes CI, where for Siren, it was failing. And that's where we try to converge that, where for both Siren and Runc, we set those properties unconditionally. And we recently got that merge, and it's out in Siren 1.25. So there was one more thing where there was a difference in both Runc and Siren in terms of how they used to calculate CPU shares and CPU weight. Runc was calculating using the quadratic expression for the conversion, where Siren was using the linear one. Both were right, but then both the maintainers came and come to the conclusion where we need to use a single formula to convert the CPU shares. And that's where in 1.33, we fixed that for both Runc and Siren, and we have that change in place for both Runc and Siren. Now, the lessons that we learned from this is both the runtimes having the same features might behave differently. And that's where the feature parity comes into picture, where the behavior is very important. And how you can actually track that behavior with the help of the real workloads and the testing around that. I know there's a possibility where there are few edge cases where you cannot resolve, but you can certainly take that as a lesson, and probably next time if you want to do those kind of testing, you take the lessons from the previous one and try to fix that one. I'll give you one more example, not related to difference between Runc and Siren, but very interesting one. It's around the perf and scale testing. So we encountered this issue in OpenShift, which is like the enterprise-ready Kubernetes, but I'm open to talk about that. So in this case, it's not about how Runc and Siren work. So it's mostly about the cascading effect that happened when we actually fix certain things in Kubernetes and the container runtime interface. So just to give you a background, CNV is the container native virtualization, and KubeVirt was actually using Siren as the default runtime to spin up VMs on top of OpenShift. Now in 2025, around April, there was a CVE around thermal side challenge thing where the containers can access certain thermal paths and can do sophisticated side channel attacks. So in order to mitigate that, what we did in the upstream Kubernetes, we tried to mask those thermal paths, and we did do the same thing for container runtime. Now, what happened in that case? Like, we tried to fix the CV for the Kubernetes and container runtime, but we didn't take into consideration how that is going to impact CRUN. I mean, you might question here that, probably for the normal test, it wouldn't matter. But when it comes to perf scale, where you are actually doing that, you are deploying like high density deployment, let's say 50 plus or 100 VMs on a cluster, that's where you actually encounter that issue. So here is the QR code if you want to read about the RCL, like what really happened. I just want to briefly cover as to what was the actual fix that we made in CRUN to make it work. So CRUN was actually using TempFS to, so in this case, like we were actually masking the path inside the containers. So let's say you have a machine where you have 16 cores. It actually has 16 thermal paths that you're mounting against that particular container. So when you have 50 containers, you will have 800 paths. So it grows exponentially. Earlier, we thought it's probably because of the resource exhaustion, but that wasn't the case. It's because of the kernel level incompatibility, where the thermal directories are not the static file system directories, but they are special kernel FS objects. And there's a case where the inode information for that is a little different than what we basically use that for the static one. So after much research, we realized we can change that approach and use bind mount, where we'll have a shared directory. And we'll have one shared directory and the bind mount where you just have the pointers. And that definitely solved the issue that we were hitting for the CNV1. We can go through that RCA to get more information. So the idea here is like sometimes it's hard to actually catch these issues in CI because performance and scale testing jobs are expensive in terms of resource and compute. And what we have decided is to run at least on the release branches once, so we can encounter certain issues, but still there is a gap that we need to identify. So here what we did, we made the change, we challenged the system, then we understood what's happening, we fixed it, and we learned from this particular one. And that's how we are here to share that experience to grow and build a community around it. Now, looking back at this, like, when it comes to runtime, like what lessons we learn, what lessons actually learn and what this thing basically taught us is we need to test deeper. Agreed, like, need to cover a bunch of test cases. There's a room for improvement. Obviously, we need to take that into consideration. We need to also validate the life cycle and the tear down parts. And why it is important, like recently there was a discussion around making Conman RS as the default monitor for CRI-O. For those who don't know, Conman is the container monitor for the container runtime. And the Rust implementation is a little superior. Like we re-architect everything, and we also made few patches to make sure we get some better improvement. But having said that, looking at the lessons, we wanted to do some more thorough testing to make sure we battle tested against everything, so we don't leave any room for the future edge cases. I'm saying that, but probably there might be a case, but at least what lessons we learned from CRUN, we don't want to repeat the same for the next default that we have. Now, enough about lessons. I think let's talk about the interesting project that we inducted recently, like last month, that is CRI-O credential provider. So this plugin is based on the upstream Kubernetes 1.26 feature, that is kubelet credential provider. So the most important problem that we are trying to solve with the Kubernetes clusters is how to pull images securely in a multi-tenant environments without using the node-wide static credentials. So what this plugin does, it actually fetches dynamically the credentials with the namespace that pod that belongs to, And it then creates the temporary path under CRI-O auth. And it's a temporary one. It's not like it will be there forever. So it expires after a certain time. One good thing about this is we made CRI-O secure, flexible. At the same time, every namespace will have its own credentials. And that is something which is really important. It's a small change, you can say, but it definitely solves the pain point that we've been facing for a long time. If you want to learn more about it, there's a reading where there's one more feature that is coming in 1.34, that is beta by on, where you can actually create the service account for the credentials. So here's the architecture. I don't want to go into details, but this architecture, the left part is for the OpenShift one. But the gist of this architecture is that the kubelet asks CRI-O for the image pool, then CRI-O requests the credential provider to get the credentials, and those credentials automatically get expired at some point of time. So this change is transparent for the workloads, lightweight and scalable, which is where this solution is much better than what we used to do for the static node level static configuration, and that was something it's like a pain point for us. So, what are the use cases and the future roadmap that we are thinking about this? So, as I said, like for the multi-tenant clusters, we have namespaces, and for each namespace, we have the credentials. So that is something which is really helpful. We also think about the pull image for the image registry and the pull through caches, where we can certainly use this one. And there's a use case where you need to rotate the credentials. And this might be a very good use case to use this plugin. Here's the work in progress roadmap. It's not fixed, but since it's a new plugin, we need your input, we need your guidance. We want to hear once you start using it, and we need more feedback. But we are thinking about adding some secret backgrounds, and observability and debugging is also there in the card. And we want to make sure that we expand this registry across the ecosystem. All right, I think this way, I'll hand it over to Ayato. We'll cover the rest of the presentation.
Yes. Next, I'll discuss recent Signal initiatives, particularly those related to container runtimes. Understanding the relationship between Kubernetes enhancements and container runtimes will help you grasp how we handle those enhancements on CLI side. The first one is in-place pod vertical scaling. This feature enables us to update pod resources like CPU and memory in place without restarting. Some workloads have like long-running and stateful, for example, AI training jobs. These jobs can be restarted easily because it would require another lengthy run from the beginning. For this enhancement, new CRI API, update pod sandbox resources, was introduced. We supported this API in 1.33. With this API, users can add domain-specific logic in the container runtime via NRI plugin. The second one is container stop signals. This feature enables us to configure custom stop signals instead of a seccomp. And CRI-O respects the new field stop signal and uses it if it exists as a step signal for container. And the third one is CRI for container and pod stats enhancement. Currently, pod and container metrics are collected by kubelet, or more specifically, collected by CAdvisor code integrated in kubelet. This cap will move those metrics collection for pod and containers to container runtime, and kubelet will only collect node-related metrics. We expect this change will reduce the risk of inconsistencies between a kubelet and container runtime, and also eliminate wasted resources from redundant collection from both sides. It also enables us to gather metrics from non-container workloads like VMs. There are some missing metrics on the container runtime side, so we are working diligently on implementing them now. As you can see, some Kubernetes enhancements have CRI changes, and we are continuously adapting CRI-O to the new CRI specifications. And this is one of the most notable features in CRI-O recently, OCI volume source. This feature enables us to mount OCI objects, such as OCI image or OCI artifacts, as a volume on the container. This is a native Kubernetes feature, and you can use it out of the box in 1.35. It works with any OCI-compliant registry, which is a significant advantage because you don't need any persistent volumes or extra containers to use data from OCI objects. The only dependency is a registry, which you're already using when pulling images. No third-party tools are required, and also you can use image tags to version control for version control. Also, you don't have to think about caching or garbage collection because they are both managed by kubelet. Using the OCI volume source feature is straightforward. All you have to do is add this volume spec in the pod spec, and that's it. Let me briefly explain about the difference between OCI images and OCI artifacts. Both fundamentally follow the OCI image specification, but there is a big difference. Images have an image config, while artifacts don't. As a result, images are runnable container image because image config has some required configs like commands or environment variables, something like that. But artifacts, on the other hand, lack these configurations and are not runnable. There's also a difference in how layers are structured. Images have multiple layers that together represent a container's file system. But artifacts layers usually represent individual files. Because of these different layer structures, CRI-O mounts them differently. When mounting an image, we use overlay file system to stack all layers into a single unified structure. When mounting an artifact, we use bind mounts for each individual file. This is the usage of artifact. It can be used as ML models, configuration files, and also static assets. And there is a sandbox project, CNCF model pack, which trying to define open standard ML model based on OCI artifact. Now, I'm going to show you some demo where I run Olama with GPT-OSS model backed by OCI artifacts. I have one single node cluster, and it runs CRI-O, recent CRI-O version. And this is the artifact I'm going to use. This has multiple files, and some of them represent models and models, parameters, license, and also this is a config file for Olama. And I already pulled the OCI artifact because it will take some time to pull because it's too big. First, I'll start from the pod without volume. So I can prove that this container doesn't have any models right now. See, this doesn't show any models, which means this image doesn't have model. And next, I'm going to create a new one, which has volume mounts. And this is the artifact. And create a pod. And if I run Olama list, it shows a model. And with that one model, yeah, we can run LLM model. Yeah. And you can see the mounted artifact by running mount command. As you can see, there are 6 files mounted in the .olama path. Okay, yeah, that's all. So next I'm going to talk about CRI-O's future roadmap. I encourage, if you're interested in CRI-O's future roadmap, I encourage you to explore our future roadmap here. And we welcome contributions and feedback from the community. Let me highlight some of the exciting features we are working on. The first, we are considering expanding more support for OCI artifacts, such as signature verification support, and also automatic tag extraction. Also, we are focusing security enhancements. Recently, we added config to for security audit for privileged containers. Also, we are undergoing security audit by CNCF. Finally, we are considering adding performance testing in CI to ensure CRI-O performs efficiently at scale. These are just some of the highlights. I encourage you to check out our roadmap or like CRI-O issues in the GitHub. Yeah, this is the GitHub link and Slack link if you're interested. Thank you for listening. That's all.